Right, in this video we're looking at something that would feature in the electropotentials topic. There are different types of questions they can ask regarding electropotentials, and this is a slightly unusual one, but actually it's a really good one, I think, for helping us understand some of the key features of electrochemical cells. So if we start with what we've got here, we've got two half cells. So the half cells are the metal and the solution, and we complete the circuit in two ways. We've got the salt bridge, and the salt bridge will always have to be soluble. It'll be a soluble ionic compound. Your safest bet is to go for potassium nitrate. All group 1 ionic compounds are soluble, all nitrate compounds are soluble. And then the other part of the circuit features a voltmeter, which interestingly, compared to anything you would have done in physics, whether that's A-level or GCSE, the voltmeter is in series, whereas voltmeters are always in parallel whenever you've used them in physics. If we look at the half cells themselves, they feature the same metal, copper, and they feature the same solution, copper sulfate. Now, what we're really interested in is the sulfates are essentially irrelevant because this is an ionic compound. This copper sulfate is ionic and it's aqueous. That means those ions are completely separate from each other. So what we've really got in the solution are copper 2+ ions, but in different concentrations. So the only difference between them are the concentrations. If we can continue with what they're telling us before we start any of the questions, so the questions don't really start until after this piece of information. It's telling us that the student recorded an initial voltage of plus, and that's quite important, 0.16 volts at 25 degrees Celsius. So the 25 degrees Celsius is telling us this is a standard condition. One of the things about standard conditions is that's 298 Kelvin, which would be a standard condition temperature, or is the standard condition temperature. And we're going to assume it's the same with pressure. Okay, so standard temperature and pressure. Now, what else? So the fact it's positive, and the way that they've set up, we know that whenever we do a E-cell calculation, it equals E right minus E left. Okay, and so our E right here is clearly is the right hand half cell, and E left is the left hand half cell. And the fact that we have a positive value, that's telling us that the right hand half cell is positive, or it's more positive, I should say. So these are relative. We're talking about them relatively speaking. So relatively speaking, this is the more positive, and this is the more negative. Okay, so the right hand side is the more positive, and the left hand side is the more negative. Now, how could we have anticipated that? Could we have maybe thought about that ahead of doing this question? I think we could have done. So what we've got in each of the half cells is an Equilibria, and we will write the Equilibria, and I'm going to put the state symbols because that's important here. I'm going to write the Equilibria as they're presented on the electrochemical series. So you have the oxidized species on the left and the reduced species on the right. And if we're comparing, if we compare the two half cells, the difference between them, as we've already said, is the concentration. So in the left-hand half cell, we've got a concentration of 0.15 moles per decimeter cubed of the copper 2+ ions, and we've got 1 mole per decimeter cubed of the copper 2+ ions on the right. So if we look at the Equilibria and we think about the position, if we're looking at the left-hand half cell, we have a lower concentration, right? So if we think about changing from the right hand half cell with the 1 mole per decimeter cubed to the left hand half cell with 0.15 decimeter cubed, then we are lowering the concentration. And if we lower the concentration, the position of equilibrium shifts to the left to sort of compensate for that change. Now, if we're shifting to the left, what we're doing is, in effect, according to this equilibria, is we are releasing more electrons. Now, it's important to think about where those electrons are going to be. Those electrons are going to be on the solid or on the electrode, right? That's where those extra electrons are going to be. So we can, if we were comparing the number of electrons on the metal, if we compared the left and the right, because of this shift to the left, because of the reduced concentration, we would have many, many, many more electrons. Put all those minuses there, compared on the left compared with the right. And it's that difference that is the potential difference. So if we've established that we've got the positive, and we didn't need to do that equilibria bit there, we could gauge it from this, but I think it's useful for appreciating some other aspects of electrode potentials to have looked at how the position of equilibrium might change things. We've got a more positive on the right, more negative on the left. If a current is to flow, or a current is a flow of charge, the charge that can flow, at least as far as this part of the circuit is concerned, is going to be those electrons. Where are they going to flow? Well, they're going to flow towards the positive side. So we would expect that if the current was allowed to flow, that it would flow in this direction. So flow of charge. I mean, it should make sense that you expect electrons to go towards a positive side, I would hope. Now, of course, they don't actually flow, not in this setup anyway, because of that voltmeter. And it's important to remember that a voltmeter is in effect, so I'm not saying it's literally this, but we can think of it like this, in effect, an infinite resistor. So we are measuring the maximum potential difference, but the current isn't actually going to flow with when the voltmeter is in series. So the voltmeter is in series for a purpose, really. It's to be able to measure the maximum difference, the maximum potential difference between those two half cells. Okay, so that's sort of a lot of background information. I hope it made sense. I'm going to write actually on the salt bridge, I'm going to write what we might use. I think your absolute go-to is potassium nitrate. You're going to be careful of any other salts that you go for. Don't go for a chloride because the potential problem you've got there is if you had a silver half cell, then those chloride ions and the silver ions would form a precipitate, and so that would cause a problem. So occasionally they might have a question where they have a salt bridge and they have something like, I don't know, sodium chloride, and they could ask you what a problem could be, and you've got to check, do you have something that the chloride ions could interact with? And so if you have a silver half cell, then you could get a precipitation, you get silver chloride precipitation, which you know from your Group 7 part of the course, and that would cause a problem when it came to this. But principally, the reason we have a salt bridge, which is our first question, is, so it says, explain how the salt bridge provides an electrical connection between the two solutions. Explain how it completes the circuit, in effect, is what it's asking you. And really, it's no different than a sort of GCSE answer. The ions are free to move through it. So remember, current is a flow of charge. When it's physics, we're really only interested in or focusing on electrons that move through wires, that move through metals. But of course, when we've got chemistry, if we've got an aqueous solution with ions in it, then they can also move, and that is a flow of charge. So the ions are free to move it. That completes the circuit. That allows the current to flow. Okay, the next question. It tells us that the standard electrode potential for the copper 2 plus copper electrode is, and then gives us the half equation, and then gives us the electrode potential, which is plus 0.34. Now, our clue here is that they're telling us that this is the standard electrode potential. Now, we've already established that the temperature is at the standard, under standard conditions. It's 25 degrees, or more accurately, 298 Kelvin. We're assuming the pressure is, atmospheric pressure, room pressure, so that's all okay. But what it's also telling us here is the other part of the other sort of standard condition, particularly with electrode potentials, is that we have solutions where the ions, and the ions that we're interested in, so in this case copper 2+ ions, have a concentration of 1 mole per decimeter cubed. So what that is telling us is that the electrode potential value for this half cell, the one on the right, which has the correct or the standard conditions concentration, is going to be plus 0.34. We know what the overall electrode potential is. It's plus 0.16. And so we're going to be able to work out the value for the left hand. So we start with our general expression, E cell equals E right minus E left. We want E left on its own, so we're going to add E left to both sides and subtract E cell from both sides. So E left equals E right minus E cell. We know that E right is 0.34. We know that E cell is 0.16. So that means our electrode potential for our left-hand cell is 0.18. Okay. Both electrodes contain a strip of copper metal in a solution of aqueous copper 2+ ions. Well, hopefully you're already aware of that. And then it asks, state why the left-hand electrode does not have an electrode potential of plus 0.34. And that boils down to what we recognized here, the fact that the concentration is not a standard conditions concentration, so we just merely have to put the concentration is not 1.0 moles per decimeter cubed. Okay, fairly straightforward, hopefully so far. You may wonder why I was doing all that preamble at the beginning, but it's partly to sort of give you a bit, make sure that these videos aren't just simply here are the answers. Now we've got to do the conventional cell representation, the conventional representation, good grief, for the cell. Include all state symbols, right? So lots of people forget. I've even seen students underline something like that and then actually forget to do it. So one of the things to remember is that when you write a cell, you write it where it's reduced, oxidized, oxidized, reduced. And in fact, what we've got is each one of those, that's the half cell, the RO, so reduced and then oxidized. Then we have the salt bridge, which is what's denoted by those two lines. And then we have the oxidized and then the reduced. Now they're both copper and copper 2+. On the outside of your conventional representation for the cell, there must always be a solid. So if you find that your reduced and oxidized species are not the reduced is not a solid, perhaps it's a gas, then please make sure that you have a platinum electrode on there, so that you've got a solid at that end of the cell diagram. But for this, we've got copper and copper 2+. So this is actually a fairly straightforward one. I guess you could be slightly thrown by the fact that they're going to appear to be mirror images of each other, the two half cells. But we've got copper, which is a solid. We have a phase boundary. So a phase boundary, a simplistic way of thinking about it is it's a difference in state, but that's not strictly true. It means there's an actual boundary between the species. So to give you an example of two things that you would think of as being in the same state but having a physical boundary, a phase boundary between them, if you think of oil and water, so they're both liquids, but they would actually have a boundary between them, so we would need to use a phase boundary if that was relevant to our diagram. So we've got solid copper Then we've got our copper 2 plus aqueous ions. That's in our left-hand half cell. Then we've got the salt bridge. And then we've got exactly the same, but remember it's reduced, oxidized, oxidized, reduced. And so we end up with that. And that, to be honest, is probably the easiest cell diagram you might have to write in an exam question. Okay, so the next question, it's only 2 marks, but in a sense this is also part of the point why there was a bit more preamble when we started this question. So it asks, or says, sorry, when the voltmeter is replaced by a bulb, the EMF, or the electromotive force of the cell, decreases over time to 0 volts. So essentially the potential difference decreases to 0. Suggest how the concentration of copper 2 ions in the left-hand electrode changes when the bulb is alight. Give one reason why the EMF of the cell decreases to 0. So we've got to give, we've got to basically explain, we've got to give the change and then explain the change. So let's just go back to the diagram. So I have written that the direction of the flow of charge. But one of the things that we said, though, that is when we have the voltmeter there, that's in effect an infinite resistor. So even though we have a potential difference, even though we have a direction that the flow would, the charge would flow in, we don't actually have a flow of charge because there's an infinite resistor preventing that from happening. They have replaced the voltmeter with a bulb. Now, that is still a resistor, but we are able now to, the charge can now flow. So the charge is going to be flowing in this direction. So if we look at our Equilibria, for example, and we look at the left-hand cell, we've got electrons flowing away from the left-hand half cell. In effect, then, we can say that the electrons in our Equilibria is decreasing. And so where does the position shift? The position shifts to the left to replace those electrons, to counteract the change. In doing so, what happens to the concentration of the copper 2 plus ions? They increase. So when we think about what's happening, we are, when we put the bulb in there, the electrons in the left-hand half cell flow towards the right-hand half cell. So the number of electrons in this Equilibria decreases because they're moving away. If we get a decrease on that side of, on the left-hand side of the Equilibria, the position will shift to the left to counteract that change, to produce more electrons, as it were, to replace those that have gone. In doing so, though, our concentration of our copper 2 plus ions is going to increase. So when we come back to that question, the change in concentration, the concentration will increase. Okay, so then it asks us for the reason why the EMF decreases to 0. So this is an extension of our answer to the previous part where we've said the concentration will increase. So again, if we just go back to the original diagram, we've established already that the concentration here is going to increase. So what happens to the concentration on the right? Now in this on the right, what we're getting is we're getting more electrons, so they're arriving. So our electrons are increasing. So our position of equilibrium is going to shift to the right to remove those electrons. In doing so, the concentration is going of the copper 2 plus ions is going to decrease. So what we've got happening here is we've got the concentration on the left-hand side increasing, the concentration on the right-hand side decreasing, and they will continue to increase and decrease until they become equal. So, because then once they become equal, but once these two concentrations become equal, once the left and right concentrations become equal, there can be no potential difference, and therefore there is no flow of charge, and therefore there is no further change. So our answer to this one is that the concentration of copper 2 plus ions So we will represent it like that. In the two half cells, the two half cells will become equal, and once they become equal, there's no potential difference, there's 0 volts. So I think this was a good question in terms of just getting your head around the actual electrochemical cells and how changing conditions affects things. And I hope that was useful.